lesson 2.6. As we get going here, I'm going to tell you a couple changes I've come up with. Not that it's going to really affect you a ton unless you want it to. Is first on Google Classroom. If you go to Google Classroom, I know some students have said they wish I did use Google Classroom, and I came up with a way where I can use both. So if you want to stick with PowerSchool Learning, that's great. Starting on chapter 3, if you want to use Google Classroom, you can. If you go to classwork, you'll see down at the bottom, I have these links that I was required to put up for the math department. But at the bottom, I have chapter 3. And I might just move that to the top because that's where we're going to be going next when we start up next week. All the links that you need from everything in here will be within this. So like for 3.1, when we start that lesson, if you click that, you'll notice that this will look, once it loads here, through Google Classroom, you'll get the same little window that you've had in PowerSchool Learning. If you remember, everything I've been giving you has those number 1, 2, 3, and 4. This has the same thing. You can submit your lesson exams right through there. If you click that number 3, you'll be able to submit your lesson exam. So I've figured out a way just to link all of it together. So if you want to use Google Classroom exclusively, because maybe all your other classes do, you can use it starting with mine, starting on chapter 3. That's how that'll work there. Just to compare the two. This is second period, just so you can kind of see how they compare to one another. From here, normally you're used to this window where I have the 4 things we go through. We take attendance, I teach, you submit your lesson exams down here, and then number 4. Well, now I'm doing it through Google Classroom where you can click the link. It'll open up this Google Doc with the same 4 things to do, and you can submit your lesson exams from here as well. Great, so if that helps you out, great. If not, it's no biggie. So that will start with chapter 3. Chapter 3 is going to be next 9 weeks when we get going there. Today is lesson 2.6. So if you go to chapter 2, go down to 6. We are going to be using these Desmos Graphs exclusively today. And I'm not going to give you all the answers. A lot of them I'm going to be expecting you to do. So I would hope that you go ahead and click that. I'm going to give you a moment to do it. If you're listening later to the video, just pause your video at this time. Click here for my YouTube playlist. Then click here for Desmos Graphs. So under number 2, the 3rd bullet, click that Desmos Graphs link right there, so you can follow along with me. So let's take a look at number 1. It says Brent, dealing with the blood disorder diabetes, must keep us closely monitor my blood sugar. If you don't know, that's my first name, so I made this poem about myself. So after eating a meal, I start to digest the food. What happens is I take in blood sugar or take in sugar from my blood, and my blood sugar goes up. Now, what happens if I don't eat? What starts happening to my blood sugar? It's going to end up going down. What this is saying is there's an equation to model my blood sugar there, where T is in time and hours. If my blood sugar needs to stay at a level or remain higher than 80 or greater, about how much time can I wait before I eat another meal? So the thing about word problems, I mentioned this on lesson 2.4. We didn't really get into it on 2.5, but 2.4 we did, is I said the key with word problems, if they give you an equation, is just to identify what the variables represent. So here at the front, I have an S of T. I want you to read the problem and find out what does S of T represent. What does S of T represent? It came somewhere in this problem. Blood sugar. So I'm going to box this up so we can keep track. Blood sugar is S of T. So S basically stands for sugar. It makes it easy to think of it that way. S is for sugar. Okay, there's also this variable T. What does T represent? Time. T is time. So what I told you in 2.4 is if you have a word problem, find your variables and box those up so you're not confused. Then look for the value that's given to you in the problem. There should be some mathematical value that we can plug into the equation. What is the mathematical value they give us? $80. Now what is 80? Is 80 a time or is it a sugar level?
Sugar level.
It's a sugar level. So that means 80 is going to go in for S of t. So if you pull up your Desmos graphs, I said I already had listed, that 80 is going to go right there. You could try to solve it by putting 80 in the front. Let's see if Desmos gives us an answer. So here's that first graph. When you open it up, it should look like this. You can try putting an 80 here, but it's not going to give you an answer. So here's the way I taught you to do it on lesson 2.4. Is so you have S of t there. Is I said, whenever you're solving these problems with the equation, to divide the equation, if Desmos doesn't give you an answer right at the start, you divide it at the equal sign. And we do y equals 80 and y equals this side. And so I'm going to graph those and look for the intersection. So I come back over here, and I'm just going to type in y equals 80. And I could change the S of t, or I could just leave it. But since I did on the other page, I'll just put it as a y. You don't have to change that. And you look at the intersections. Now, last class, I told you something very important about real-world problems. With real-world problems, specifically when x is time and y is your blood sugar, what values are not relevant to the problem? Negative. Negative times? Can we have negative time? No. So anything where time, x-axis is negative, this part of the graph you can ignore. All that is ignored. What about with blood sugar? Can your body have a negative blood sugar? What's the lowest amount of sugar you could have in your blood at any time? Zero. So anything down here is irrelevant. Now, why does that matter? Because this limits our graph, and not only that, it's going to remove this piece. Now, I'm going to switch colors. This piece is going to be removed because here's what happens. If someone's blood sugar gets down to a value of 0, right there, if a blood sugar gets down to 0, the person's going to be dead. Did you know that? If blood sugar equals 0, you have no blood sugar in your body. Guess what? You're dead. Okay, so this is talking about me, and this problem I made about me very specifically, so no one would take offense when I say this. If I die at this point in time, doesn't matter if a few hours later someone comes by and injects me with some sugar. Is it going to change me? Am I all of a sudden going to come back to life? Or am I still dead? Dead. That's why I scribbled out this part of the problem. After I die, nothing else is relevant. Said another way, once this graph leaves the first quadrant, nothing else matters anymore. So this is the only part of the graph that matters. Specifically, we said in the problem it needs to be at 80 or higher. So I think the question said, how much time can I wait before I eat another meal? So I eat right here. This is when I eat. I eat at time 0. And what happens as my body just digests the food, I get more and more sugar. So the sugar doesn't enter, though it enters my body right away, it doesn't enter the bloodstream right away. You have to digest it, right? And so it rises, it rises, it rises, and then it falls. What you need to find out is how much time does it take before I got a problem? And that's that intersection. I'm going to let you work that problem. I'm going to pause this video here. So if you're working on at home or listening not live, you just need to pause the video. So that's the x value you're looking at. This one right there. All right, let's take a look now at number 2. Number 2 says, what equation represents a slant asymptote for the graph of the function f of x equals 2x cubed minus 5x squared minus 8x plus 1 over x squared minus x plus 5. Okay, so this, I'm about to show you a graphing trick for how to do this type of problem. But before I do that, I'm going to go over the algebra again. So we learned this in lesson 2.5, that slant asymptotes or horizontal asymptotes come from the rules about checking exponents. So there were 3 rules. There was what we called EATS DC, which stood for exponents are the same, you divide your coefficients. There was BOBO, which means if you were bigger on bottom, powers, it was going to be y equals 0. And the last one was bigger on top, no horizontal asymptote. Instead, you would use division to find your slanted asymptote. Because this says slant, it's going to be this situation, but let's just check it just to make sure. Tell me about my exponents. Are the exponents the same? Are they bigger on the bottom or are they bigger on the top? Bigger on the top. This has a degree of 3. This one has a degree of 2. So it's bigger on top, which so the rule was bottom meaning no horizontal asymptote. It's slanted instead, or oblique. So here's how you find it. You use division. Can I use synthetic, meaning do I know what x equals in the denominator, or do I have to use long division because I do not know x? You look at this denominator. Could we state what x actually equals? Can I just do inside lies? The answer is no, it's 3 terms. I don't know what x equals. If you don't know what x equals, you need to do long division. So we do x squared minus x plus 5 dividing into, you do exactly what the problem shows, divide. Fraction means divide. Into 2x cubed minus 5x squared minus 8x plus 1. When we do long division, you ask yourself, what do I need to multiply x squared by to get 2x cubed? X squared times what is 2x cubed? 2x, very good. And so by the way, this top part is what you call the quotient. This is going to be the equation of the asymptote. So when I multiply this by 2x, I get 2x cubed. And you distribute 2x times negative x. What's a negative x times 2x? Negative 2x squared. Very good, Josue. And then 5 times 2x is 10x. The hard part of a long division, well, one, it's long. It's aggravating. But the tricky part is that a lot of students forget what I call the fundamental rule of division. It's when you come to this point, these don't technically cancel out right now because they're both positive. However, we know they should cancel out because what we do automatically in our head is we always switch the sign. But the thing we forget to do is you have to switch every sign. So this front one becomes a negative. The negative is going to become a positive, and this positive is going to become negative. And now I can combine my like terms. So this combines here. I get negative 3x squared. That becomes a negative 18x. And now the 1 drops plus 1. And I'm back to the start. I ask myself, what do I need to multiply x squared by to get negative 3x squared? Let's see, x squared times negative 3 gives me negative 3x squared. Do we agree or disagree with that? X squared times what gives me negative 3x squared? Negative 3. I agree, it's negative 3. So if I multiply by negative 3, x squared times negative 3 is negative 3x squared. Negative 3, you got to distribute all the way through. Negative 3 times a negative x. 2 negatives make a positive 3x. And positive 5 times negative 3 is negative 15. By the way, this up here is going to be our answer. All of this, what's left over, is going to be the remainder. But before I combine them, I got to do the fundamental rule of division. What happens to this negative? Positive. What happens to this positive? What happens to this negative? So these go away. I'm left with negative 21x plus 16. That's my remainder right there. But the asymptote comes from the quotient. This quotient right here, this q of x, that's where we get the answer. So on Alex, I believe I have you type it in as y equals. So the answer would be 2x minus 3. So, are you ready to see how to use the calculator to do this? If you had to find asymptotes, I told you in the lesson, is kind of like end behavior. It's talking about what's the graph doing on the very ends. So an asymptote should match the end behavior, not necessarily the middle behavior, but the ends of the graph. So if you come over to your Desmos, I'm going to unclick those 2 graphs, and I'm now going to turn on, that right there is number 2. There's the graph of number 2. So I'm looking at this picture. We said the answer is y equals 2x minus 3. Now I told you this is like end behavior, not middle behavior, but end behavior. So when I look at them close here, do they look exactly the same? By no means. But if I start to scroll out, this is where what asymptotes do. They model what the graph is doing when you zoom it out. You see when I zoom out here, how similar to these two graphs now look on the ends. Not in the middle, but on the ends. How similar do they look? Do they look pretty close to the same thing?
Yeah.
You see how close they are? If you were taking a multiple choice test, and I'm going to change this color so I have them. Okay. Which color most represents the purple graph? All right, you ready to see them all? So we want to know which one best represents the purple. If it was a multiple choice, I just made 4 different options. Would it be this blue? Does the blue represent it pretty well? Does it kind of on top of the ends, or is it off? It's off. There's gaps. Okay, what about this one? Is it on? What about this one? Is it on? What about this one? Yeah, so you see the cheap way of doing that on a calculator is you just grab an asymptote means the end behavior. If you look at the ends of the graph, they should be just about the same thing. So it's not the middle of the graph, it's the ends of the graph you'd be looking at. Questions on number 2? So you have those 2 answers. You can go ahead and submit those into lesson 2.6 if you would like. Just go over here, lesson 2.6, open up your exam, and you can submit your answers as you go. We just got the answer here, which I'm not telling you, but this one I did tell you. It's 2x minus 3. Make sure you don't have any spaces, and then we're moving on. Okay, I'll set that off to the side. Let's get started with lesson 2.6. Oh, I have some review problems real quick. Just to make sure we haven't forgotten. Key things I want to hit. When you're looking at fractions, this is going to be very important later today as well. When you talk about domain, what's the one rule with, not one rule, there's 2 rules of domain. What are you not allowed to do with division in mathematics? What are you not allowed to divide by? 0. So when we talked about domain last class, that was the first thing we talked about. I said define your domain. You set the denominator as not being equal to 0, not x, I'm sorry, x plus 2. X plus 2 cannot equal 0. So what's my domain on this problem going to be? If the inside lies, what can x not actually equal? Remember, inside lies, so instead of it being a plus 2, it becomes a minus 2. If you're wondering why is that, it's because to get rid of the plus 2, you have to subtract. That's how I get that. So that's my domain. X cannot be negative 2. What makes a vertical asymptote is if you can cancel it. Or, sorry, what makes a whole is if you can cancel it. If it cannot cancel, it's a vertical asymptote. Can that x plus 2 cancel with anything in the numerator? Does it cancel? Is x minus 2 the same thing as x plus 2? Same or different?
Different.
They're different. So does it cancel?
No.
No. So number 2, you call it a vertical asymptote. And as I just said a second ago, an asymptote means it's basically the end behavior. If you zoom out, that's what's going to be happening at that spot. We have an asymptote at x equals negative 2. So it's the same breaks in the domain that create the asymptotes and the holes. So at negative 2, here, or the domain, we're saying the domain is not equal to negative 2. That means there's a break. What type of break is it? It's a vertical asymptote, also known as an infinite discontinuity. So I'll throw that in there. It's an infinite discontinuity. And it says also find horizontal asymptotes. Horizontal asymptotes would follow the rules. Are your powers bigger on top, bigger on bottom, or are the exponents the same? This one's a little weird because it's in factored form. If I multiplied this out, I'd end up with an x squared on top and an x on bottom. Are we bigger on top, bigger on bottom, or are the exponents the same? Bigger on top. So this would follow the bottom rule, but I'm not going to do another one like that. Well, yeah, I'm not going to do another one like this. You would use division, but we'd have to FOIL that out. So I'm just going to leave that like that. Since I already reviewed one like that, I'm going to skip the horizontal part. Okay, and now I'm going to show you from a standard view. How would you do it if it was in standard form? Well, this we'd have to factor. So I'm going to ask you, when I have to factor this, does the top share anything? Is there anything shared in the numerator?
The 9x.
I hear 9x. So they both have a 9x. There is something shared, but it's not 9x. They both don't have. They both have an x. So g of x is going to equal. It's the same thing as x times x squared minus 9. So I divide each term by an x. I factored that out. That's a GCF right there. What I just did. Greatest common factor. And on the bottom, I have x squared minus 9x plus 18. And so I'm going to x method these. I'm going to do both the top parenthesis and the bottom. Now the top parenthesis, this one, I have an x squared, I have a 9, but I'm missing the x term. So I'm going to say I have a 0x there. So for this one, a times c is negative 9. My b is 0. And for the denominator, so again, that's a, that's b, that's my c. This is a times c, that's my b. For my denominator, this is my a, b, and c. So I'd have factors of 18 that add up to negative 9 there. Okay, let's start on this one, the numerator. What are, write that down. What are factors of negative 9 that add up to 0? Is it 1 and 9 or 3 and 3? Which ones could somehow give us?
It's now the end of B lunch.
You do 3.
3 and 3? I agree. But to make it equal 0?
You gotta put a negative.
3 minus 3. Good. That multiply and give us negative 9?
Yeah.
Perfect. And they subtract to give us 0. Okay, over here, factors of 18 that make negative 9. Is it 1 and 18? Is it 2 and 9?
Yeah.
Is it 3 and 6? Which ones could somehow give you a 9? 1 and 18, 2 and 9, 3 and 6. 3 and 6. Okay, to make it be a negative 9. Here, negative, negative. Well, 2 negatives when you multiply give me a positive?
Yeah.
Perfect. So we just found out it's g of x equals, we had this x up front. This means we have x plus 3, x minus 3. That's what this parenthesis became right there. The denominator becomes x minus 3 and x minus 6. So if you're going to do these same 3 things, number 1, for your domain, what are the 2 values I'm not allowed to divide by right here? X cannot, because remember you're not allowed to be equal 0. So what could x not equal right here? Inside lies.
Oh. 3.
Positive 3. What could x not equal right here?
Positive 6.
Positive 6. So domain x cannot equal 3 or 6. So that means on number 2, I need to have an answer when x is 3 and when x is 6. Now, you look at it. Can any of these cancel? Can any factors cancel? X minus 3s can cancel?
Yeah.
I agree. That can cancel with this one. That means those are going to be a whole or removable. So the one that remains is a vertical asymptote. I'm going to abbreviate. Vertical asymptote at x equals 6. So that's that answer. We have a whole at x equals 3 because that's the one that canceled. And so how you solve for a whole is you plug in a 3 to every x value. So if I plug in a 3 there, I would have 3 times 3 plus 3 divided by 3 minus 6. Let's simplify this. What's 3 plus 3?
9. I mean 6.
6. And 6 times 3 is 18. So I'd have 3 comma 18 on top over 3 minus 3 is negative 3. And so 18 divided by negative 3 is negative 3. Let me cover this up so I can write it clear. This whole is going to be at 3 comma -6. 18 divided by -3 is -6. That's where the whole will occur. And finally, if I wanted to do intercepts, I'm trying to review some of the stuff here. Whoops. This was number 4 on our list. And the Y-intercepts, what you do is you basically cross out anything that has an X. So if you cross that out, I'll go back to the original problem, it'll be easier. If I cross out anything that has an X, I'm left with 0/18, nothing over 18, which means it'll cross the Y-intercept at 0. And finally, the X-intercepts are when the top equals 0. So if you wanted those, you'd say where these equal 0. So at 0 and at -3. That would be the X-intercepts at 0 and -3. So that was a review of what we did last class, just so you can see it a couple more times. I know it went really fast, but luckily I recorded it for you. So you can go back to YouTube later if you want to see that a little bit slower.